Hello physics students. In this video, we're going to be analyzing projectiles that are launched diagonally like this. Now, before I begin, I want to first review the two main ideas about projectile motion. We learned them when we were studying projectiles that were launched horizontally from a high altitude and curved down like this. But the same principles apply to these kinds of projectiles. So what I'm going to do is I'm going to create a pause, and you're going to quiz yourself, and you better know the answer. What are those two facts? So in the pause, see if you can think of them in your head. All right, hopefully you said this, that in the y direction there's an acceleration of 9.8, and in the x direction there's no acceleration or constant velocity. So those two things happen at the same time. The y acceleration is not affected by any horizontal motion, and the horizontal motion is not affected by the y acceleration. They happen independently. Before I begin with the notes, I just want to show you another demonstration that'll demonstrate those two principles and their independence. So I have this device again configured in a different way, and what it's going to do is prove two things for projectile launch like this. One, it's going to prove that the vertical direction motion is not affected by any horizontal motion, and the horizontal motion is not affected by the acceleration in the y direction. In other words, constant velocity this way, acceleration this way, independent of each other. The way it works for this demonstration is there's like a little spring-loaded cannon here, and it gets released by this pin over here. And if I just go straight in slowly, you see that the ball goes straight up and straight down. Furthermore, if I wanted to, I could carefully measure the height that this went to, which is well, maybe like 90 centimeters or so. So what I'm going to do now is push this through at a slow velocity. And what we will see is that 90 centimeter vertical motion is not affected by the horizontal motion. It'll reach the same altitude. Furthermore, the x velocity will not be affected by the acceleration. That'll be proven by the fact that the ball and the car have the same x velocity, so this will rise and fall and land in the basket again. In other words, if I watch it again in slow motion, I will not only see that it falls in the basket like I saw in real time, but I'll see as we go frame by frame that the ball is always directly above the car at all times. In other words, the x not affected by the y not affected by the x. So let's have a look. First thing I'm going to do is push it through slowly. And it landed somewhere over here. Okay, so it had, again, a certain horizontal displacement, but the y altitude was the same exact as when the car wasn't moving. I'm going to push it through faster. We'll see again, reach the same y altitude, but still land in the basket and still always be directly above the car. Landed way over here. So again, proving the x doesn't affect the y doesn't affect the x. So constant velocity, acceleration, a projectile problem, therefore, is two problems happening at the same time. You have to keep all the x information separate from the y and vice versa and solve. So before we begin with solutions, I just want to just highlight with this diagram the concepts that are happening. In 1 second intervals, I'm showing velocities of something launched in a diagonal like this. It's launched horizontally with velocity 15 and up vertically with a velocity of positive 29.4. Notice that at all time, the x stays a constant 15 because there's no gravity side to side, so the velocity or the speed doesn't change. But in the y direction, I launched this way, and gravity's pulling this way, so it slows it down by 9.8 up on the way up, and then it speeds it up by 9.8 downward on the way down. So notice I'm subtracting 9.8 on the way up, and I'm subtracting 9.8s from the velocities on the way down. The entire time, the acceleration is negative 9.8. So this shows us 1 second snapshots, but what we're going to do is pull out some facts about these projectiles that you absolutely need to know, otherwise you're not going to be able to solve these problems. The first thing, notice, if these are 1 second intervals, let me count. 1, 2, 3, 4, 5, 6 seconds was the total trip of this projectile. Notice though, on the way up, it spent 1, 2, 3 seconds on the way up, half of 6. On the way down, it spent 1, 2, 3, also half of 6. So it doesn't matter how fast you launch this. If I launch this like this and it goes like that, or I launch it out of a cannon, right, it spends half the time up, half the time on the way down. So the up time, down time are half the total, equal. Notice that in the y direction, I launched up with positive 29.4, and it struck the horizontal surface with negative 29.4. So another thing you need to remember about these problems, whatever you launch in the y direction, it impacts the same speed but downward, so the minus sign and the same number. That's what this is saying. By the way, if this kind of confuses you, just write it out in words, that the y velocity final is the same number but negative at the end. So something like that. The velocity in the y direction is 0 at the peak, but the x velocity is not, right? The x velocity never goes away. It's always 15 throughout because gravity doesn't act sideways. And then, of course, these are just the two facts that I threatened you with. You better remember, right? That the acceleration is always 9.8 in downward direction, and the x velocity is always constant horizontally. Now let's see if we could take these facts. Oh, by the way, I need to create a pause to let you catch up if you need it. Now we're going to take all this information, the two facts and these little trivial things about a projectile launch this way, and we're going to see if we could solve for how far something goes, how tall it goes, how much time it spends in the air. Here's the example. A paintball gun shoots a ball 50 meters a second, 30 degrees above the horizontal. So I'm taking the gun and I'm tilting it 30 degrees up like this, right? Or really kicks back like that, and then it goes like that. So it's going to make this parabolic path as it's going the paintball. So determine the original x and y velocity, because I'm shooting up like this. So it's got an x and y velocity, the time of flight, horizontal range, and maximum height. First thing, so why do I need to find the x and y velocities? Because the velocity is currently split and mixed up in the x and y. It's doing both things at once. But remember, a projectile problem is two problems. I've got to separate out this velocity into the x velocity and y velocity so I could even begin my analysis, my two problems, my x and y problems. So I just construct a little triangle, and I can use, to find Vx, the cosine function. Remember, all calculations in Regents, on the lab, on the Regents, you have to show a formula before you begin. So I write cos theta. You could have wrote adjacent over hypotenuse, just some kind of thing with no numbers in it. Then I plug in my numbers, and notice I need my units. So yes, that 30-degree sign, if you leave that off, you get a 1 out of 2 on the Regents. Terrible, terrible. But you have to put that little degree because it is a unit. And then it's adjacent side over hypotenuse, adjacent over hypotenuse. And then I multiply 50 to the other side, I get 43.3. All right, so let's move on. But if you need a moment to catch up, I'll create a pause to allow you to copy that down. Part B, the time of flight. Oh no, I didn't finish. I got to get Vy. So that's this side over here. Notice it's the opposite side, and I have the hypotenuse, so I'm going to use the sine function. Once again, I've got to write a formula first. Sine theta equals, this time maybe I'll be consistent. Vy over V, the opposite side over the hypotenuse. Plugging in my numbers. Multiply 50 to the side, and I get Vy equals 25 meters per second. Okay, take a look. Does anyone see why I got an F on this problem? Why I failed it according to the Regents grading scheme? Right, now it's my turn. Bad, right? So don't leave that off. You get a bad grade, a really harsh grading. All right, so let's move on. Part B, the time of flight. So in the diagram I erased, you saw that the x velocity had no bearing on how high it went. That was how fast you projected upward. So the y velocity, or the y direction calculation, is what determines the time this thing spends in the air. So part B, the time of flight, what I'm going to do is now just remind myself, you don't have to write this out when you're solving, but put it in your notes so that you kind of know what's going on. We're stuck in the y direction. That means we better not ever use this number, right? Because we now got to fix our mind to the y direction, think about what's happening. So I launched this projectile up with 25. So what I have to realize is that if V initial is positive 25, that means when it's coming back down, the V final is negative 25. See, nobody's going to tell you that. You just got to remember that for these kinds of projectile problems. And you have to remember that the acceleration is negative 9.8, and that we're looking for the time. So we go to our reference table. Where's my reference? Oh, all the way over here. So we're in the mechanics section, the back, page 6, if you will. So that now, if we go down here, the formula that includes the two velocities, the acceleration and time is right here. Vf equals Vi plus At. So all the formulas for projectile motion you're going to find in here. So let's begin by writing the formula, because again, that's another way we get a 1 out of 2 if we don't write the formula first. So let's make the Regents grading happy. There, okay? Now we're going to plug in our numbers. All right, by the way, maybe you need a moment to catch up, so I'll create a pause to allow you to catch up. Moving on, let's plug in the numbers. The final is negative 25, so the initial is positive 25. So that goes over on this side of the formula, positive 25. And then the acceleration is negative 9.8. So rather than doing plus negative, I'll just do minus. And time is the variable. So I subtract 25 from both sides. That'll give me negative 50 on this side and negative 9.8 t on this side. Dividing both sides by negative 9.8 gives me approximately 5.1 seconds. So shoot that paintball, right? And then 5.1 seconds later hits the ground. The next thing that it asked, I erased it, let me check here. The horizontal range, where did that paintball land? So now horizontal, of course, now we're in the x direction. So that means we better not be using this. This is in the y direction, right? The x direction velocity, v initial, x, not y. I erased it over here, the little triangle. It was 43.3 meters per second. And by the way, so is the final, because the acceleration is 0 in the x direction. We also know that the x motion stopped in 5.1 seconds because when it hits the ground, it stops moving. And we're looking for the distance. Question mark. So we get out our reference table. We look for a formula that has VI, acceleration of 0, time, and distance. We look back here. So here we are. Oh, let's get the focus going. Okay, here we are. And it's basically coming down. This formula right here. Now, the acceleration is 0, so we could actually leave that part of the formula off like this and just write d equals VIT and lose no credit at all. That is acceptable because we determined that part of the formula is 0. So let's write d equals VIT, and I'm not even going to write that part. So now, again, I better not use the 25 or even the 50 that went up like this. I've got to use the x velocity. And then 5.1 seconds. Punch that on a calculator, and you should get 221 meters, I believe, is what I got. Maybe I'll even put an x. Why not? Right? D in the x direction. All right, so let me create a pause in case you need a moment to catch up. All right, one last part. The maximum height the projectile reached. Now you have the diagram maybe right in front of you, but I erased it already. Remember, we had this diagram of like this, right? So it took 5.1 seconds to make the complete journey from the moment this ball was launched upward. What you have to realize is that at maximum height, right here, the time to get there was only half of the 5.1. Or the time to fall was 5.1 seconds over 2. Or 2.55, if you will. So what we could do is we could either find the distance that the projectile rose, and that would give us the correct answer, or we could find the distance that the projectile fell, and that would also be the height that it came from. It turns out that it's easier, a little bit easier, not that hard to find this, but it's a little bit less calculating if we find this distance. So what I'm going to do for part D is, first of all, remember that I'm in the y direction. That's the maximum height, y direction. And I'm going to find the distance of the fall rather than the rise. And then what I could see is that when the projectile begins up here, the VI is 0. If we, VI equals, you say, wait a minute, I thought VI was 25. Well, yeah, if you call this the initial point. I'm starting here now. And at that point, the y velocity is 0. X isn't, but the y is 0. So V initial is 0 in the y direction for that falling part. I know the acceleration is negative 9.8. I know the time is 1/2 of 5.1. Well, you know what? I'll write it here. I won't be lazy, or 2.55 seconds. And I'm looking for the distance in the y direction. So I'll go for the reference table again. I'm not going to bring it up to the screen again. Maybe I'll make you a little too dizzy just coming forward and backward. So remember that it's D equals VIT. And this time I could leave that part off because VI is 0 plus 1/2 AT squared. Plug my numbers in. Maybe I'll, because I need a little room here. 1/2 negative 9.8. Punch that on a calculator, and I think I got 31.9. Negative 31.9. But remember, that's how far it fell, which is basically how high it rose. So I don't want to say it rose negative 31.9. That kind of sounds silly. It doesn't make sense. So we'll say maybe H, the height it went, was positive. Well, I could even leave the positive off. Just say 31.9 meters. That's how high it went at maximum height. All right, so let me create a pause in case you need to catch up. All right, so that's projectiles launched at an angle like this, following that curved downward parabola. Remember, all of this comes from those two facts about projectile motion, right? The two facts, right, that you know now, right? I hope you know. Constant velocity in the x direction, acceleration in the y direction. Keep the data separate, and then do a kinematics problem with acceleration like this, and a kinematics problem with no acceleration, constant velocity that way. And then solve the two together, get the answers, okay? And a reminder, the key thing for the time in this case was this formula for time. You don't have to write it down because it's in your notes, but go back in your notes and circle this for time. And then for the x dx, circle this, VIT for the x, and make sure you're putting your x velocity in there. Those are the key pieces of information in this kind of projectile problem. All right, I hope you enjoyed the video. I hope you weren't scared by the threats, but I hope you remember those two facts about projectiles and how to use them. I'll see you in the next physics video.